working of this oscilloscope, right? Right, thank you. So, here you can see that the very first knob that you are seeing on the left hand side, that is intensity. Okay. Now, using this intensity you can make it brighter or you can make it little dull. Okay. Right now, for the purpose of showing in the recording, I have kept the intensity maximum. Okay. But please remember that that is not a good practice, because whenever you are doing the experiment, just adjust the intensity according to your ambient lighting condition. Okay. If you are working in a room where there is ample of light, okay, as it is, because here for the purpose of recording we are using lots of studio lights, okay, there we need to increase the intensity. But if the ambient light is on the darker side, then even if you keep a very small intensity, there is no problem. And it is good practice to keep the intensity small, because that extends the life of the phosphor of the screen. Okay. This is the screen that you are seeing. I will be coming to the screen little later. Okay. So, the first knob is the intensity, which you adjust exactly according to your lighting condition. If you are satisfied that the beam is visible, just stop it there. Do not try to unnecessarily keep the intensity on the higher side, because it may not be good for your eyes even. So, make it very soothing to your eyes. And then the next knob is the focus. So, you will see that if you are changing the intensity, then even focus also gets changed. Okay. You can see that I can make it out of focus, or I can make it exactly, I mean according to the focus. So, when you need, you can adjust this focus button also. Okay. Now, I will be showing you some more facilities which we will be requiring. You see, just come to this particular knob. Okay. This knob is marked as the X position, so that we can adjust the starting position of the beam, and accordingly using this we can make this beam move towards the entire set of things, can move towards the left or to the right. Can you see that using this knob I can shift it horizontally, I can shift to the left, or I can shift to the right. So, this is, I mean, sometimes according to our viewing requirements, we may have to adjust this position. Okay. Then you can see that there are two more positions which are available. I mean, actually these two knobs which you are seeing, or these two channels which you are seeing. Now, here this is the waveform of the waveform which we are feeding for the channel number 1, and this is the waveform that we are feeding for the channel number 2. So, channel 1 or channel 2 means the two beams that I was talking of, the beam A and beam B, which I was referring to while giving you the lecture. So, now you can see that there are individual set of controls which are available. So, on the left hand side, all the controls are pertaining to this channel, and on the right hand side, whichever controls you are seeing, these are pertaining to this channel. So, they are independent of each other. Okay. And right now, since I am concentrating only on one beam, okay, you can see that there is a button called Y position. So, using that I can move the beam up or down. So, clockwise the beam is moving up, anti-clockwise the beam is moving down. Can you see? Okay. So, we want to view it maybe at the middle, because there is only one beam present. So, good to adjust it near the middle, so that we can see the waveform properly. Okay. Now, you can see that a very crucial thing over here, here there is a triggering knob. Okay. And this, I mean there is a selection switch which are available, and you see in I mean different positions the triggering may differ. Like this is one case where there is no triggering. Can you see that the beam is not being made stable at all? So, you need to trigger the oscilloscope. You keep it in this position, this top one, which is actually marked as the AC, and here it is exactly triggered. So, once you find that it is exactly triggered, do not try to disturb the setting. Okay. you will see that there is also a fine adjustment. Just in case you find that nothing is working, okay, you can adjust the level of the trigger, but normally it is auto triggered, so you may not have to bother really, okay. But in cases in case you need to, okay, just fiddle this, but do not try to fiddle this much, okay. Now, this is the times per division scale, okay. This is a big rotary knob, and I tell you the range of the oscilloscope is that you can monitor waveform even in the megahertz range, or you can monitor the waveform even in few hertz of range, okay. So, I can keep turning the knob, and if I turn to the left, you will see what happens. Say I turn one step to the left, can you see that we are seeing more number of cycles? So, here what I have done is that from 0.5 milliseconds per division, I have moved to 1 milliseconds per division, which means to say actually we will be having more number of cycles which will be there, because 1 milliseconds per division is a much longer thing. So, now this waveform, for example, let me tell you that here I have fed from the signal generator, I have fed a 1 kilohertz signal. Now, I just move the beam so that I make little adjustment with the horizontal and the vertical. My idea of doing it is so that the starting gets aligned exactly with this marking. You see, if you are able to, I do not know whether you will be able to see it on the screen or not, but this oscilloscope screen, they are having some graduations or some scale markings are there, okay. If I can explain to you, there are 1, 2, 3, 4, 5 large divisions on the left hand side. This is the center of the screen, 5 large divisions on the right hand side, and similarly on the top to bottom also 1, 2, 3, 4 large divisions at the bottom, 1, 2, 3, 4 large divisions on the top, this being the center, and these are gridded. The oscilloscope screen is gridded, and it is being gridded to for your convenience only, so that you make a measurement using these grids, and all these major grids, they are further sub-partitioned, that each grid is having 5 sub-partitions, okay. So, they are sub-grids or smaller markings which are kept, and that is there on the horizontal side, that is there on the vertical side also. Now, whenever we say that the timing which we are indicating here is 1 millisecond, it is this buttons actually the knob is now pointing towards 1 millisecond per division. It means to say that these big graduations which are there, so it is exactly 1 millisecond, every division, every large division corresponds to 1 milliseconds of time. So, which means to say that because we have got 5 here and 5 here, that means to say 10 divisions completed from here to here, from the left to the right, 10 divisions are completed. So, we are actually displaying the waveform for a duration of 10 milliseconds, okay. Now, I have fed 1 kilohertz sine wave. So, within these 10 divisions, I should see how many? I should see then 10 complete cycles of the waveforms, because it is kept in 1 milliseconds per division and there are 10 divisions. So, there should be 10. How many? Let us calculate 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Can you see? It is 10. So, that means to say that we have I mean really fed a 1 kilohertz, and whether we have fed 1 kilohertz signal or not, that can be ascertained from our measurement also. You see, one cycle of the sine wave, that is taking 1 division closely, it is 1 division, but this setting is giving you 1 milliseconds per division. But if I make it little longer, perhaps my observation will be better. If instead of 1 millisecond, I go over to 0.5 milliseconds. Now, can you see that one cycle takes how many divisions? 2 divisions. So, these are up to here, from here to the to this point, again when it traces the next cycle, there are 2 divisions which are completed. So, 2 divisions means what? It is to be, this 2 is to be multiplied by 0.5, because it is 0.5 milliseconds per division. So, 1 millisecond. So, 1 millisecond we complete 1 cycle. So, definitely it is a 1 kilohertz sine wave. You will see what I will do is that I will slightly change the frequency. I have changed the frequency. Now, you see that this is my 1 cycle, this is my 2 cycle, and how many divisions it is occupying right now? 1, 2, 3, in between 3 and 4. So, it is not exactly 3, it is not exactly 4, but the smaller markings which are there, it is falling in the second smaller marking. Second smaller marking means there are 5 small markings. So, which means to say second, each small marking corresponds to 0.2. So, then second smaller marking means 0.4. So, that means to say that 2 cycles have exactly covered 1, 2, 3, 4, 3.4 divisions, or if we observe even more closely, let us say that I make it one more step, it is 0.2 milliseconds per division, and one cycle takes exactly 1, 2, 3, 4, 4.3. So, 4.3 milliseconds is 4.3 divisions are there, and it is to be multiplied by this 0.2. So, which means to say that 0.86 milliseconds, and 0.86 milliseconds you can see the reading 0.86, if you take the reciprocal of that, that comes very closely to 1176 hertz, okay, or something close to that. So, which means to say that as we are varying this frequency, can you see that how the cycle changes? We make it 2 kilohertz, okay. We make it 2 kilohertz, and now we are having 0.1 milliseconds per division, and can you see 5 divisions are exactly covered, 5 large divisions are covered by one cycle of the sine wave, which means to say 0.1 into 5, 0.5 milliseconds is the time period, and 0.5 milliseconds corresponds to 2 kilohertz, and our reading is 2 kilohertz, 1999, that is almost 2 kilohertz. So, this is the way whereby we can adjust the time, okay, and there is a facility or a provision to adjust the voltage also, okay. Now, let us see that how you adjust the voltage. You see, just similarly here times per division, which is being controlled by the sweep generator, this is volts per division, and right now we are in 1 volt per division position, and this thing can be changed, because we have on this side up to 20 volts per division, and then here if we go this side, then the volts per division decreases, and we can go all the way up to 5 millivolts per division. So, from 5 millivolts per division up to 20 volts per division. So, it is a very large range, can you see. So, now right now it is in 1 volts per division. So, if somebody asks us to exactly find out or measure that what is the voltage, what we will do? Now, we will measure that how many vertical divisions are there, okay. Let me adjust the voltage slightly, okay. You see that here this top one, 1, 2, 3 divisions. So, from the 0 level up to the peak over here, it is taking 3. Now, how do we find out the 0 level? Well, that is also a very important thing to know. You see, there are 2 knobs here, ground and AC. If you are keeping it ground, then it will give you the 0 level. So, it is a good practice that you keep the 0 level to the central line. This is the horizontal central line, and you remove the ground, then this is the 0 level, and then with this 0 level you can see that it is occupying 1, 2, 3 divisions, and this is 1 volts per division. So, this corresponds to 3 volts amplitude. So, it is going 3 volts this side, and this side also it is going 3 volts. So, it is 6 volts peak to peak signal, we know. Okay. Now, if we change over from from 1 volts per division to 2 volts per division, what will you expect? Obviously, you will expect that the signal will be shown with a as if to say a smaller amplitude, because instead of 1 volts per division it now becomes 2 volts per division. So, 6 volts peak to peak will now be shown by 3 divisions. Here it is shown by 6 divisions. If we go to 2 volts per division, you can see that peak to peak signal is shown by 3 divisions only, 1.5 this side, 1.5 this side. So like that we can keep varying, and as our signal amplitude changes, okay, like I am increasing the signal amplitude, okay, in such cases, okay, I have to keep adjusting the knobs, and if my signal is too small, okay, then I will have to, I have a second beam, and I will just explain the purpose of the second beam little later. Now, you see that I just make the amplitude smaller. So, in order to make it visible, I have to keep going to the right. I make even smaller, I keep going to the right. Okay. Now, you see that here I can go only up to 0.2 volts per division with this signal. If I want the signal to come down, as I was showing you earlier, that I just put the attenuation, and this is what the signal level will be, and this is a smaller signal. So, adjustment is little difficult, even triggering also has become little difficult thing, but anyway we can always make those adjustments. So, this is the volts per division function, and very similarly we have for the other, and here you see that how to feed the signal. I just show you here. You can see one connector. These are called as BNC connectors, okay, and this is, I mean, what I have in my hand is actually a BNC plug. So, one end I have connected to the signal generator, and other end of this plug I have to just feed it. Feeding it is very easy, because BNC is a very nice kind of a connector. You just plug it in, it goes in one direction, and then turn it on the right. Okay. You will hear a click sound, and this is very firmly attached. Usually these things do not have contact problems. So, even if you move slightly here and there, of course you should not do, but even if it is done accidentally, the contact will not matter much, because it is quite a good connector. And like this we can feed the second signal also, and let me show two signals being fed simultaneously. So, what we are doing here is that we are feeding beam 1 and beam 2. Now, the two are not having identical volts per division, and let me just adjust the amplitude and bring it. Okay. Can you now see that I have two beams, beam A whose control I am having with this knob, beam B whose control I am having with this knob. So, two beams are being shown simultaneously, okay, and using this I can change the times per division, using this I can change the volts per division, and now why we require two beams simultaneously? As I was telling you that it is always recommended to monitor both the input signal and the output signal simultaneously. Maybe that input you have fed a beautiful sine wave, but you are conducting experimentation with some amplifiers, and your amplifier is clipping the signal. So, the output you will not observe as a sine wave, you will see the output as a distorted sine wave, or you may see it as a clipped sine wave. So, in order to verify that, in order to find out that, what you need to do is to keep adjusting, or you have to simultaneously monitor the input and the output. So, for that only this facility is being given. Okay. So, we are monitoring two waveforms, and let me also tell you that there is another good purpose of doing it. You are not only comparing the input and the output waveform, but even you can do phase measurements with this also. How you do the phase measurements? You see that for both the beams, the identical times per division holds good, as I was telling you. So, if you see that in this case, of course, we have fed the same input signal to both channel A and channel B, okay. But supposing the output is phase shifted with respect to the input, in that case what we can do is that with reference to the input, after how many divisions, after how many horizontal divisions the output waveform is starting, okay. If you can measure that, you can say that what is the time delay between that, and by knowing the time period of the waveform, okay, you can convert that into the phase difference between the input and the output. So, this is some kind of a facility that you have. And now I can also show you that how to measure the rise time of the waveform, because sometimes whenever we are carrying out the experiment with square wave, like in your experiment series only, you have some measurements that involves square wave, where you will see that you have to measure the rise time of the waveform. Okay, before I go into that, let me tell you that sometimes what you need to do in a typical circuit based experiment, which you will require even here also, that is to say that supposing we want to study the response of the circuit from very low frequency, let us say from 100 hertz of frequency, I want to study that what is its response up to, let us say 100 kilohertz or 1 megahertz. So, what we need to do is to feed the signal from here, okay, and then observe the output waveform of your circuit on the oscilloscope. So, you may see that as we keep increasing the frequency, up to some time the gain of the amplifier is remaining unchanged, okay. Maybe up to 1 kilohertz, up to 10 kilohertz, the gain has not changed at all, but maybe after 10 kilohertz, whenever we increase the frequency further, the gain starts falling. So, we can measure that, and that is called as the frequency response, which we will simultaneously do using the signal generator and the oscilloscope. And the input waveform remains the same, the input signal remains the same, we keep that as undisturbed. We keep the amplitude of the input undisturbed, and we see that how the amplitude of the output that changes, that gives us the gain, that is output by the input, which we express as the decibels. In dB we express that. So, in dB we can calculate that what is the gain versus frequency, and we can do such measurements using the oscilloscope very easily. So, that is one way of finding the frequency response, but whenever we are doing the measurements using square wave, okay, square wave pulses we feed, okay, how do we measure the response of the circuit? Say if the circuit is like an RC circuit, what will happen is that there will be a finite rise time, okay, and as a result of the rise time, the shape will not be, the output waveform shape will not be exactly a square wave, but rather it will be and there will be some exponential rise, because we may be taking the output across the capacitor. So, there will be some exponential rise of the waveform, and we are interested in knowing that how much time it takes from 10% to 90% to attain from 10% of the level to the 90%, that is defined as the rise time. And why we go from 10% to 90%, why not 100%? Because if it is exponential growth, you know that theoretically the exponential signal will reach the 100% of the value only at time infinity. So, that is why rise time is defined up to 90%. So, how do we find out 10% to 90%? Okay. Do we very painfully keep measuring with the volts per division and try to find out that exactly what it is? Okay. No, actually there is a very good facility using which we can do the rise time measurements, okay, which I will show you right now. Okay. So, let me go over. So, we will cycle of a square. I don't know whether you are able to see it on the screen properly. Is it visible on the screen? Okay. Now, I adjust its voltage. Okay. You will see that here in this oscilloscope screen there will be two dotted line marks. Okay. You may not be able to see it on the screen, but whenever you take the actual oscilloscope, you will see one dotted line is marked as 0% and there is another dotted line on top which is marked as 100, and you will see that just above this dotted 0% line there is a firm line which is marked as 10, and just below the dotted 100% mark there is a firm line that is 90. So, actually what you have to do is that you have to bring your waveform, that is to say you have to make it merged with this dotted line. But how do we actually adjust the upper voltage to bring to the exact 100% mark? So long we were using the calibrated buttons, and the only case where we can decide to go from the calibrated to uncalibrated is just take this red central knob. So long we were not changing the red central knob. Okay. For adjustment of the voltage we were only changing this coarser knob, but this is a finer knob and there is a position to the extreme left where this is the calibrated position. So, remember all your measurements, your volts per division will be valid only with the calibrated positions of this knob, but to measure the rise time we make a special exception of going over to the uncalibrated. So, if I turn this knob, it goes into an uncalibrated mode. So, can you see that I can continuously adjust its span. So, now using this uncalibrated button and this horizontal position simultaneously, okay, let me bring the lower mark to 0% and the upper mark to 100%. Okay. And then I will keep adjusting the time. Actually, you see that here it is with this thing going positive, this thing going negative, I can change the polarity entirely. Okay. I can make the negative first and positive later using this plus minus button. That means to say that the triggering, instead of being done with the rising edge, is now being done with a falling edge. Okay. And you see that using this X position I bring it somewhere here. Okay. And by again making this timing also uncalibrated, it is possible for me to adjust. Now, I cannot show you the rise time, that how much is the rise time, because here this signal is fed from the signal generator and it is with a very good rise time, almost 0, almost ideal rise time is there. But maybe in your RC circuit certainly it will have a finite rise time which you will be able to measure, because after adjusting, supposing your waveform goes like this, like an exponential. So, you can find out that how much time it takes from 10% to 90% of the marks. Okay. Find out their difference, then multiply it with the times per division and you will be getting that exactly how many divisions you take in order to measure the rise time. So, this is for the rise time measurement. Okay. So, these are the functions which you will be using. Actually, oscilloscope may be having lot of other sophisticated features also, but all of this you will not require. Okay. Another important thing possibly you will require is this ground. Ground, I already told you that using the ground you can adjust this level. So, there is a small blue button, you can see this is ground, and here this is a button which is marked as AC. Okay. The difference between AC and the DC coupling of the oscilloscope is that using the AC coupling, actually any DC voltage which will be riding on the AC, that will not be shown. Like say for example, I am having a sine wave, let us say 3 volts peak to peak sine wave, okay, whose lower edge is at 2 volts peak is at 5 volts. So, it makes a swing between 2 volts to 5 volts, a sine wave that goes from 2 volts to 5 volts. So, you can easily calculate that its DC level is 3.5 volts. Now, in the DC mode of oscilloscope and AC mode of oscilloscope, what is the difference? The difference is that in the AC mode you will be you will not be showing that 3.5 volts of DC. Okay. Instead, it will be brought down to the 0, the DC will be brought down to the 0, as if to say that you are passing through a capacitor. Internally the oscilloscope will pass it through a capacitor so as to block the DC, and then you will be observing, because it is a 3 volts peak to peak, you will be observing the waveform from minus 1.5 volts to plus 1.5 volts. Okay. Even if you adjust the DC offset, supposing now instead of 2 volts to 5 volts I make it from 7 volts to 10 volts, what all that I have done is to add the DC offset to it, but in the AC mode I will not be able to measure that DC offset at all. But if I want to measure the DC offset, then I have to go to the DC mode, and actually this button, this blue button AC, which is marked as AC, okay, you will see that below that there is a marking which is called DC, okay, which will be visible in the actual oscilloscope definitely. So, here you can see that AC is with a longer marking of the button and DC with a smaller marking of the button. What does it mean? If you keep it unpressed, then it is AC, and if you keep it pressed, okay, then it is DC. So, right now there is no difference between the DC and the AC, because we are not feeding with any offset, but in your circuit if you have to measure the DC voltage, remember that you have to press this and then only the DC voltage can be operated. So, this is the DC and AC, and then here we are observing two channels, right. So, we are observing the channels like this, that this is the yeah. So, these are the two channels. Let me just put it as the so these are two square waves. Okay, never mind, I can make it sine wave also. Okay. So, this is, so both the channels are having two the identical sine wave. Now, there is a button which is called as channel 1 oblique channel 2, okay, and if it is on the outermost side, okay, then it is channel 1, otherwise it is channel 2, but this is the source of the trigger. Means sometimes you have to keep one signal as the reference. If you are keeping, let us say, the channel 1 signal for as the reference for triggering, then you will keep it on the outer side. If you want to trigger with channel 2, then you have to keep it on the inner side. So, this also can be pressed or kept unpressed, like that. And these are the two knobs which will be used by us. This you can see that it is a dual. This button is marked as dual, and I have pressed it. Why I have pressed it? Because I want two channels to be displayed. That is why I have pressed it dual. And if I just unpress it, that means to say dual button outside, can you see that only one channel is displayed? Again, if I press it, I can show both the channels. So, this is the purpose of the dual. But you will notice one difficulty with the dual mode, that is to say that once we go over to a smaller frequency, okay, I will do that. I will make the waveform. Now, I have made it a 283 hertz signal. Okay. Now, I think that you can also make it out. There is a flicker that goes on in the display. Can you see? There is a flicker. Okay. Now, that kind of a flicker you will not observe much when only one channel is being viewed, but two channels there is a flicker. Actually, you know how the two channels are displayed. I was explaining the mechanism of the oscilloscope to you, where I was telling you that that goes from left to the right, and then again it goes from the left to the right using the sweep. Now, in the when two beams are to be displayed, we display it in the alternate mode. Alternate mode means that one trace will be for the beam 1, that is channel 1, and the next trace will be for channel 2. So, alternately channel 1 is being shown and channel 2 is being shown. You are seeing the simultaneous effect as a result of the persistence of vision. Okay. But alternately, first trace channel 1, second trace channel 2, again third trace channel 1, fourth trace channel 2, like that. This is called the alt mode. But in low frequency, there is a problem with the persistence, because you can see that because the time period is now too high, okay, 283 hertz means that time period has become considerably on the higher side. Our persistence of vision is getting disturbed, and we are observing flicker onto the screen. Now, how to make the screen better? Okay. For that, there is a chop mode which is available, and chop mode will require that next to dual there is another button which is called as add button, and if you press these two simultaneously, okay, then it is at the chopped mode, and there is little bit of a triggering problem. Okay. I mean, make it at some other frequency. Now, you can see that here, okay, that sort of a flickering is not there, but the moment I make it in the dual mode, in the alt mode, there will be flickering. So, chopped mode, what happens, you know, that there beam 1 and beam 2 we have to show. So, we just while the beam 1 goes on, we make a time partitioning. For a small amount of time we show beam 1, followed by small amount of time for beam 2. Again we switch to beam 1, again we switch to beam 2 within one trace itself, so that simultaneously you show both, and your effect of flickering is eliminated. So, that is why at low frequency it may be a good practice to use the chop mode. So, these are the overall functionings, okay, and even in your website, the manuals of the oscilloscope and the signal generators which you will be commonly using, those are also uploaded. So, now I mean, after listening to this lecture and demonstration, you will be in a position to even go through, your advice to go through the catalogs which are uploaded in your Intino website, and then you will have a better understanding. So, we hope that with this kind of idea, using the instruments like the multimeters, the oscilloscope, the function generators, it should be at your fingertips, because you will be needing these things with almost every experiment that you